Hello everyone, so this is Xuanze Zhou. So today I'm going to present a paper. It's about the target attacks on teleoperated surgical robots, dynamic model-based detection and mitigation. First of all, I would like to acknowledge the author of this work. The work has been done by the dependent groups focused on research, design, validation of highly available, reliable, and trustworthy computing system and networks. The researchers has two main branches. One is in reliability and security, and the other one is in-house analytics and the system, and they are located at UIUC. So here below is the research labs links, and you can find more materials related to what we presented today there. So so first of all, let's talk about the overview of this work, or the problem statement. Robotic surgical system, they are one of the most complex cyber physical systems, especially in the medical industry. Right now, there are like 50% of the surgery they are being conducted by surgical robot, and experts expect that 30% of the future surgeries are going to be done by surgical robot. And past studies are primarily on security attacks on communication channels rather than control systems. With malware, attacks on control system is possible and it's difficult to detect without understanding the robotic dynamic system. Dynamics model-based detection is critical for mitigating those attacks. So first of all, let's take a quick look of what the robotic surgical system is. It's a human-operated robotically controlled system which composed of teleoperation console, like this one, robotic control system, and a patient-side car like this one. And where the most of the attacks happens is the electronics control system, and its primary task is receiving the surgeon's command, translating the surgeon's command, then provided video feedbacks of the surgical field inside the patient's body to the surgeons through a 3D region on the teleoperated console, like what the surgeons see here, and also perform safety checks to ensure safe operation of the surgical robot. And on the right is the surgical robot, prototype surgical robot, which we are going to discuss today. So it's composed of instrument, which is the tool work on the patient, and it has those instruments. They are driven by the direct current motor, and it's supported by robotic arms. And here is the robotic control software and hardware, basically communicating with the robotic arm and the instrument through motor encoders and the motor control commands. So here is a detailed look of what's the architecture of Raven 2 robotic surgical platform. So on the left, you can see that's kind of the hierarchy of the controls. Human operators interface with the master console, and meanwhile interface with control hardware like the haptic sensors, monitors, and both those they are directly communicating with the control software. And the control software send and receive together with the control hardware, send and receive informations with the physical robot, which include actuators, sensors, and instruments. On the right is more detailed on the communications through the whole systems. So the desired position orientation mode, they're sent to the control thread through some sort of networks, and meanwhile the joint position robotic state, they are sent through the console the surgeon is working on, and they're together after perform the safety check is communicated to the middleware through ROS, which is a robotics operating system, and it's also it's a real-time operating system. And through this real-time operating system, it's send a motor command to the USB interface board, and meanwhile the USB interface board send the encoder feedbacks to the real-time operating system. And the USB interface is the one which directly interface with the motor controllers and encoder readers. So here it has a lot at the control hardware level. It has a lot of safety things like the watchdog, e-stop, and the pedals, which we are going to take a look here. So the first layer of safety mechanism is the safety button, which is e-stop. And the second layer is the physical pedal. So once the pedal is up, which means the surgeon releases his feet from the pedal, everything frees up. On the control software, it regularly performs safety checks by comparing the current command with a set of predefined threshold to make sure the patient's safety. And also there's a periodic square waves watchdog signal sent through the PLC to make sure the robot is in a healthy state. Next, we are going to take a closer look on the control software and the possible attacks. So here is the kinematic chain in the Raven 2 control software. The way to look at it is follow the arrows. So first of all, the control software pull out the data through USB on what's the current robot state. Basically, those signals they're from the encoder's reading, and then we convert those readings to states. And then we forward those information like motor positions, motor velocity into a forward kinematics. So through this, you know what's the attitude, what's the gesture of the robot, and then together with the result from the forward kinematics and the surgeon's command. It goes through inverse kinematics to calculate what's the next motor position, and we compare the next motor position and the current position, and use a technique called PID control, proportional integrating differential feedback control, to figure out what's the torque we needed to send to the robot, and the torque, of course, is converted to current, and then we detect whether there's any overcurrent issue, and then send all those information to USB. So through the whole process, there's attacks on different layers. It can happen on the master console, control software hardware, and also the physical robot. The target it can attack on the circuit communication, mass, and the interface. On the mass, for example, the kinematics use a lot of mass, and the interface, there's an interface between the USB and the control software. Different kind of malicious action can happen, like a change of port number, the packet content, and they can add a drift to the input output, change the robot state like what we have here, and change the command and encoder feedbacks. As a result, the impact can be hijacked trajectories like unwanted state, homing failures, and abrupt jump. And all of this has potential to lead to a stop. So it's an unwanted state one if the surgeon is working on the surgery. And the primary focus of this research is the injection of unintended user input, like what we have here, and injection of unintended motor talk commands. So for the following discussion, we will mainly focus on this two parts. So here is a break introduction on the attack scenarios for unintended motor talk commands. So first of all, the attackers download a malicious shared library which implements a write or read system call wrapper, and then attackers modify the preload command to force the future processors linked to the malicious library. Then the system call wrappers sniff USB traffic sent by ribbons and forwards the USB packets contents to the attackers listening on a remote server. And so this part is called the attacks preparation. And next is the attack deployment, where attackers download and modify the shared library. And then attacks will be triggered automatically when ribbon control software reach the pedal down state, which is the as we mentioned earlier, if it's in the pedal up stage, they will not receive any commands. And then the control command feedback send through the USB channels is modified to cause a sudden jump of the robotic arm or cause the control software to stop. And beyond the deployment, the attacker also do the offline analysis, where the attacker performs the offline analysis on the sniffed USB data from several runs to find the field in the USB packet that represents state of the robot, which we'll talk more about it later. And based on the analysis, the attackers modify the malicious wrappers to trigger attack when the robot is in the operation state, basically pedal down state. So this is how they do the attack launching and how they do the offline analysis. So basically, they take a bunch of the sample bunch of US packets collected in one run of the robot, and then by analyzing multiple runs here, they can discover best zero switch among 8 different values in surgical runs. And then the attackers combine this information with knowledge of the state machine during the tele operation, and the attackers can deploy it during the non-e-stop and the pedal up states. Because if they deploy something in the e-stop or pedal ups, and nothing going to happen, and it just disclose the malware. So what's challenging about this the detection of those kind of attacks? Direct attacks, it's a direct attacks on robot control software. So no actual process involved. Performance is uncompromised until the launch of the attacks. No changes made to the existing control flow we described. No change made to the command syntax, and it's also very sharp, quick attack within 1 millisecond. So what's the research did is that they developed this kind of environment, which include a attacked injection engine, a master console emulators, a graphics simulator, control software, and a robotics model. And the attacked injection engine, it can perform system calls, provide to perform various injected value and various at various activation time. So so here is the overview of the dynamics model-based detection. So first of all, what is being modeled? The thing being modeled is 3 motors and two rotation joint and 1 translation joint. And how is the motors and the joint modeled? They are modeled by 2 sets of second order ordinary differential equations, and the method for solving those equations are called first order Runge-Kuttas, and another one is explicit Euler method, and both of them they are calculated they're implemented in C++. Why is challenging? It's mainly because the limited computational resource and time. As we so for this model, it need to be performed on the microcontrollers, which means limited computation resources, and it also, as we mentioned, the attack happens at 1 milliseconds level, so we needed to calculate the result quickly. So on the right is the performance of the model. As you can see, in general, the error rate is within 3%, and it's efficient because we know when the attack happens. Usually it's more it's abrupt changes. So 3% is pretty good for this type of application. So the performance. So basically, as we mentioned, we are mainly looking at two type of like attacks. One is the abrupt the injected error values, and the other one is the other one is what happens when at a different attack activation time. So for injected error values, we by comparing the dynamical based model with other attack detection method, it can detect really small value, and overall it has a higher like detection rate than any other method. In terms of attack activation period, you can see we have the dynamical based model has way sensitivity at a smaller attack activation period, and also overall it has a better better detection rate. So the takeaway message is that dynamic model-based detection and mitigation mechanism excel at both the case when injection error value is small and activation period is short. Another way to look at the performance. So here is a summary provided by the author. The gist is that dynamic model-based economic detection has a better preemptive detections. Dynamic model-based method, they detect 152 more cases in injection of an unintended user input than the Raven safety check. Dynamical model detects 84 more cases in unintended control motor torque commands than Raven safety check. So the takeaway message here is that Raven safety check cannot detect all the adverse scenarios. And upon the detection of the potential adverse impact, the impact of those attacks can be mitigated by either correcting the malicious command control command by forcing the robot to stay in a previously safe state, or stopping the command from execution and put the control software into safe state. So conclusion here, with this presentation and the research, the architecture of the cyber physical system of a teleoperated surgical robot are introduced. The anatomy of target attacks against the control system of a teleoperated surgical robots are discussed in depth. You see there's a lot of control diagrams were discussed, and attacks on Raven 2 are demonstrated, and the corresponding impacts are evaluated. Defense mechanism based on dynamical system is presented and evaluated within the real-time constraints of the control system, which is the key challenge for detecting those attacks. So this is all I have. Again, I would like to thank the authors for this work again, and thank you for listening.